Welcome everyone. Today's lesson is entitled Transformations of Functions Day 1. It actually should be noted right off the bat here that we're going to be investigating 10 transformations over these next 2 days. We're going to take a look at 6 today and 4 tomorrow. Now what I tried to do as best as possible for you was organize and structure this notes worksheet in a way that you would not only understand it as we're going through it, but that if you were to look back upon it a day or 2 or 3 or whatever later, that you would know exactly where to look and know what to do from where you're looking. So we will see if I was able to do that for you. Only time will tell. But you'll see the same format on the day 2, kind of trying to keep it as organized as possible throughout the entire lesson. All right, so that being said, let's go ahead and get into our investigation. It says use the following parent functions to investigate 10 transformations of functions. Sounds good. Now these are the most basic of these particular families of functions. Now it should be noted we can use any particular function as what is called a parent function and then transform it from there using the rules that we're going to see over the course of the lesson. But these just work very well visually. They're simple to use. So that's what I'm going to do. So anyway, if you would, let's go ahead and not take too much time on this. Let's just draw these in so we know y equals x squared looks like that. So our most basic quadratic and our basic cubic. Okay, the absolute value one, that's a good one to use on some of these. I'm going to try to use my discretion and pick the ones that really work well visually, especially as we're initially investigating these transformations. So square root one actually works very well in a couple different transformations, so I'll be using that. Here's a nice exponential growth model, kind of looking like that. Probably won't use y equals x all that often, but no reason why I can't. And same with the 1 over x as the basic rational function. The graph itself is a little more complex, so it's not as great visually, so probably won't use that all that often. But again, we'll see. And then lastly, cube root function is a good one visually, so that would be the inverse of the x cubed function, and looks kind of like that. So I said nothing special here, just these are different families of functions and the most basic functions in each family. So what I need for you to do, though, is grab your graphing calculator, because we're going to go through the process here as we build our little table. And this is where I tried to be as organized as possible for you. So notice today we're going to be looking at 6 transformations. And this is the key column right here. This is where I'm going to start the process. I'm going to give you the notation. And from the notation, we're going to have to make some decisions, input or output. And what will we do to the equation itself, and as a result, what's going to happen graphically. So the way I like to think about transformations, it's kind of like a cause and effect. So we're going to initiate a change on the equation. And when we initiate that change, it's going to have some type of transformational effect on the graph. And so that's, you don't have to necessarily put that in, but I like thinking about it in those terms. All right, now I'm going to get going right away here with the notation of number 1. And then we're going to move over here, and you're going to tell me, is it an input or output change? And also, what are we doing to the equation? What specifically is going on? And then as a result, we'll grab the graphing calculators and what happened graphically. Okay, so your first bit of notation is we are going to take the original function. Original function is f of x. So this is kind of like this. The new function, your very basic generic y here, is equal to the old function plus a constant. So new function is the old function plus a constant. All right, now as a result, looking at that notation, is this an input change or an output change? Well, if you notice, I had my f of x, which is an output, and I'm adding a constant to it. And so as a result, this is what is considered an output change. And if you're unsure, you're wondering like, why is that? When you see the input change, the contrasting the two hopefully will make all the difference. Okay, but in the meantime, it is an output change. And in very basic terms, all I'm doing is I'm adding C to the function. See if you can get that in there. And so what does that do graphically to the graph of the parent function? So I'm going to grab my calculator. You're going to grab yours. I'm going to pick one of the families of functions from up above. And in this particular case, I think I'm going to go ahead and do the square root function. I think it works well here. So everybody, if you would, let's just type in square root of x. And I'm going to close that off, not that it's a necessity, at least at this point. And now what I'm going to do is take the original function, so square root of x. And I'm going to pause for a moment. So that's the original function, the square root of x. And now I'm going to add a number to it. So I'm going to take that square root of x, and this is totally arbitrary. I'm going to add 3. And the question is, what happens to the graph of the original? Well, let's take a peek. So I need you to hit zoom at the top, please. And you're going to go down to number 6, that standard window there. So you can just hit number 6. And hopefully, you'll see square root of x, and now square root of x plus 3. So the question is, what happened? How would we name this? Well, here's the graph of the original. Here's the graph of the new one. The shape is the same. It's not distorted in any way. This point moved up to here. This point moved up to here. This point moved up to here. And so as a result, everybody, this is what is called a vertical shift. The graph of the entire function moved vertically. And as a matter of fact, it moved upward. So if you can write vertical shift up, that would be great. And just want to go through that just quickly. So the entire graph right here was shifted 3 units up. And so what does that mean in terms of the original point to the new corresponding point? So here's what I wrote, and I think this is helpful. When you move vertically, C is added to the y coordinate of each point. So you hear me talk a lot about this when we do our transformations, of course. Very simply, when we have an output change, that is a vertical transformation. Anything vertical then on the coordinate plane is going to be affecting the y coordinate. Notice the x coordinates stay the same, and I'll be super quick on this. This is 0, 0 right here, right? Well, if you notice, the corresponding point is right here at 0, 3. The x coordinate stayed the same. The y coordinate, we added 3. All right, let's get into the next. So y equals f of x minus c. Also an output change. Let's get that in there. And I would say we are subtracting c from the function. Awesome. And I'm going to grab the calculator. I'll just keep the square root of x to save ourselves a little time and energy. I'm going to clear this one out though. And so, original one is square root of x. And now what I'm going to do instead of addition, I'm going to subtract a value. I'm just going to subtract 4, and probably won't shock you. There is the original, and now there is the new one. So this point moved down 4, this point moved down 4. You could see the entire graph moved down 4 units. Okay, so we would call this, of course, also a vertical shift. But because it was subtraction as opposed to addition, it moved down. And in terms of what happens to the points, again, anytime we see a vertical transformation, it's the y coordinate that's being affected. So I would say C is subtracted from the y coordinate of each point. All righty. 2 down, 4 to go. Let's get into our next bit of notation. Here's what I'm going to do. I'm going to do f of x minus c. All right, now, so how do we deal with this? First of all, is it an input change or an output change? And notice, it is an input change. It's no longer your generic x, it's x minus c. So it is an input change. How do we deal with input changes? Well, very simply, we replace all the x's in the function with x minus c. Okay, very good. And have it. Nicely done. So f of 2x looks like this right here. Okay, good. Let's go get the next set, if we can here, and start developing your input change versus output change. So let's look at letter C. So in this case, notice it's 2 times f of x. And so the question is this an input change or an output change? Am I changing x or am I changing f of x? And in this case, it looks like x is the same, right? Right in there. It was x before, it's x right now. So notice it's not an input change. What I am doing is taking f of x, I'm taking the output or the function and multiplying it by 2. So notice the difference in the notation, especially between B and C. There was f of 2x, which I called an input change, and there's 2f of x, which now I'm calling an output change. Notice the difference there, please. Now, how would you deal with this? And by the way, I should probably just above put that function just so we have that. I know it's on the front side of your page. I think I saw it was x squared and then minus x plus 3. So that should give us a bearing to do C through G here. And I guess what I'm seeing, of course, is that if this is f of x, this whole thing right here, I'm going to essentially multiply it by a factor of 2. So this says take your f of x, and this is what f of x is, of course, and just multiply it by 2. So that's exactly what I'm going to do. Those entire set of rules, squaring the input, subtracting the input, and adding 3, that entire set of rules, that entire function, gets multiplied by a factor of 2. Okay, I hope everyone sees that. 2f of x is 2 times the function. Cool. And let's distribute in 2x squared minus 2x and plus 6. Box it up, and that's great. So you're going to see, obviously, I'm going to try to really show you the primary differences, input versus output, and really see that notation in action. Okay, guys, let's go get D. So letter D, f of x plus 1. And again, I guess I would ask you, are you changing x or are you changing f of x? And in this case, I hope you all agree that it looks like we're changing x. It was this, just an x inside the parentheses. Now that x has changed to x plus 1. So it is the x that changed, and so it is the input that is changing in this function. And so as a result, this basically tells us whatever the input is, I'm going to square it, I'm going to subtract it, and I'm going to add 3. And so knowing that piece, knowing the function rules, and then knowing that, okay, this is my input that I'm going to perform my function rules on, allows us to manipulate this mathematically. And so that would be it right there. Square the input, subtract the inputs, and add 3. And my input here is x plus 1. Cool. I would ask you actually to pause the video for a sec. This is something you're going to have to be able to kind of pull off on your own. Can you guys go ahead and do this piece right here? Can you expand that out? Well, let's see how you did. I'm going to do this in 2 steps just so you can see just in case. But when I FOILed that out, you got to be careful. Remember, this is not just x squared and 1 squared. It is x plus 1 times x plus 1, which is this. And then don't forget, distribute that minus in. So I got something along those lines right there, which means I have an x squared. It looks like I have a plus x. 1 minus 1 is 0. Add the 3, and I get that piece right there. So hopefully you're able to kind of get that as well, but that's what I get as an overall answer. Okay, now notice letter E, another +1. Does this represent to you an input change or an output change? Am I changing x or am I changing f of x? And in this case, I hope you realize that x hasn't changed. It was this. Here it is up there. Come on. And it is still this right here. But now it's f of x that I'm adding 1 to. I'm adding 1 to the overall function. I'm adding 1 to the output. Excellent. And so all this means for us is whatever the set of rules would be, in this case x squared minus x plus 3, all I'm going to do, guys, is add the 1. Mathematically, it's a pretty straightforward operation here, so x squared, how about minus x, and how about a plus 4? And there you go. All right. See those differences as we will kind of work with these ideas. Letter F and then letter G, everybody. So f of negative x right there, negative 1x, I guess. Looks to me like an input change. It was x. Now it's a negative 1x. And so let's go ahead and put that piece in place if we can. And let's go ahead. How do I work with input changes? Well, very simply, if that is my input, just be careful on this one. I square the input, so I square negative 1x. I subtract the input, so I subtract negative 1x, and then I add 3. So understanding what your function tells you to do allows you to really manipulate any input. Now just be a little careful here. I will ask you to remove all parentheses when you put this in place. And notice, I'm very careful about this. This is what's being squared, this is what's being subtracted, and then I'm adding 3. So here's what I would say. This is actually a product raised to a power. Think of this as like a negative 1x, if you would. So I have negative 1 squared, and everybody, negative 1 is squared is actually just 1. So negative 1 squared is 1, and x squared is x squared. So as a matter of fact, when you remove the parentheses there, interestingly enough, it is just a 1x squared. And then minus negative 1x, so that just becomes a plus x and a plus 3. And that, everybody, is your overall answer. So just be careful on this piece. Over the years, I've seen students just have a little difficulty with that mathematics. That's what it turns out to be when you remove the parentheses. Okay, last one in this set right here. How about a negative f of x, or a negative 1 times f of x? And I'm hoping at this stage you can sort of see that that is an output change. I am changing the function. And so it looks like I'm changing the function by just putting a little opposite symbol out in front. Or really, when all said and done, just kind of multiplying it by negative 1. And that's what I'm doing, just multiplying the function by negative 1. So we're basically going ahead and distributing that negative 1 inside the parentheses there. And so this would be, watch this one, negative 1 times x squared. And that's how we would look at it right there. And then negative 1 times negative 1x, so that's a plus x. And negative 1 times 3. So it would be this right here. We will do some work on these last two, F and G, so just please see the differences and see how that plays out. This worked out this way in front. This one works out this way in front. Negative 1 times x squared. Okay, good. So I'm hoping it really solidifies that difference notationally between inputs and outputs here, and I believe we'll summarize this momentarily. Okay, so let's go ahead and summarize that, and then just do very quick little vocab work just down at the bottom there, just to get us going for the next lesson or two. So here we go, everyone. It says with an input change u, and I hope you noticed in each case, this is I guess how I would summarize it in just as basic terms as possible. So when we're dealing with an input change, we just replace all of the x values with the term inside the parentheses. Let me do that a little better for you. So with the term inside the parentheses. So I hope you kind of saw that. Anytime we sort of dealt with an input change, whatever that input was, it really replaced all the x's, and that's the bottom line. Okay? So input Just perform the function rules on that input, whatever it may be. Output changes are a little different, and here's just what I wrote. It looked like in each case we perform the operation on the entire function. So we're not replacing x's, we're not changing the x's, we're just changing the overall function by performing that operation. So that's what I pretty much wrote on my paper, and I'll do that on the board here. Perform the operation on the entire function. Perfect. And again, if you're comfortable with that previous example, then you intuitively did these pieces right here. I just wanted to summarize it for you on your notes worksheet. Excellent. We're going to kind of do a lot of work with these pieces right down below. So here's what I'm asking, see if I can fit this in here as well. But just really understanding what goes together, because you're going to really hear these phrases over and over again when dealing with functions. So it just says draw a vertical line down. Well, sorry about that. So why don't we go ahead and just match up these phrases here, what goes together in each pair. We'll get a set of 5 on the left, and then we'll get a set of 5 on the right, kind of matching it up. So let's start out, everyone. If we can go inputs, outputs. I guess you've heard me use those terms quite a bit during this lesson. So let's let them lead the way. Inputs on the top there on the left, and outputs on the top on the right. Now, as soon as you hear inputs, a variety of other things should come to mind. So it's basically just mental association with these other words on your paper, and same with outputs. So I guess the first order of business is to talk about inputs. As you've seen, they replace the x's. So why don't we go ahead and put x values over here, and when those x's go in, the y's come out essentially, or f of x. So we kind of did that with our diagram. So x represents the input, and the y represents the output. All right, very good. We're going to talk next lesson here about domains and ranges. So if you remember correctly, domain really represents all of the x values, and range would represent a set of all of the y values. So throw those together if you don't mind. And as I said, what you want to do is associate these things together and associate these things together. In terms of our algebraic modeling, of course, 2 variable quantities. If you remember from previous courses, basically the x would represent the independent variable, and then the y would represent the dependent variable. So you'll always hear it phrased, y depends on x. So y as the dependent, x as the independent. And then I guess the last one there, when we start getting into really analyzing the graphs, we'll do some of that on tomorrow's lesson with domain and range, and then in future lessons dealing with transformations of functions. Really the last set I see is horizontal and vertical. And so just don't forget, when we're talking about x values on a graph, we're talking about the horizontal component to the graph. So let's go ahead and put that one piece in. So x represents the horizontal coordinates graphically, and then of course y would represent the vertical component, or the vertical coordinates of the graph. And so we're going to analyze graphs on the next lesson, really talking about domain and range. And I'll ask you, when you hear domain, think horizontally. When you see range, think vertically. And so I just kind of putting those together. Is it a necessity? Nah, probably not. But I think it's helpful. So these things all go together beautifully, and then these things all go together beautifully. All right, nice and straightforward there, everyone. Take a little time and just work with some of the manipulations of functions. As I said, you want to perfect it before we move forward and really utilize all this stuff. Thanks for listening, and please let me know if you have any questions. Welcome. Today's notes worksheet is entitled Solving Quadratic Equations Day 1. The quadratic equation is probably the most common type of equation that we would see at this level. And some of the techniques that we're going to be using here will certainly be used in a variety of other topics over the course of this semester. So let's see if we can perfect those to the best of our abilities. Also, just one quick side note here. You will need to ask me to put the quadratic formula on your calculator. I do have that program, and I need to link it up to your calculator and get it on there. You'll need it for the second notes worksheet. So I'll remind you at the end of this one, but just in the next 24 hours or so, please make sure you have it before doing the day 2 of this, the quadratics. Okay, well let's go for it. So at the top of your page, it should say the standard form of a quadratic equation is, and so if you remember, the quadratic is a polynomial of degree 2. And that would be the standard form right there. So ax squared plus bx plus c equals 0. We've already kind of worked with this a little bit as an expression, but now what we're going to do is see it in terms of an equation and finding the values of the variable that make the equation true. So there are 4 algebraic methods that we're going to use to solve the quadratics, as it says on your paper here. Really, it comes down to factoring. I told you we've been doing a lot of factoring, and we'll see that continue. What is called undoing the square. And then I think I'm going to just have you put a little asterisk next to this one. This is, in my opinion, the most interesting technique, the completing the square. And it's a skill that we will utilize off and on over the course of the semester. So we'll kind of develop that a little today and more tomorrow. And then, of course, the quadratic formula. All right, well, let's kind of go for it. First order of business here is to take a look at factoring. So that's what method 1 is. I just jotted down a couple ideas there to solve by factoring. The first order of business is really to kind of get that quadratic in its default position there. Let's get that to 0. So before I solve any quadratics and decide on methods to use, I set it to 0 no matter what anyway. And then factor, and then we use what is called the zero product property in order to solve. So we set each factor to 0 and solve from there. Okay, well let's go for it. A, B, and C. Let's kind of pull this off. So I have x squared equals 12 minus x. First order of business is to go ahead and set this to 0. I like keeping the x squared term positive if at all possible. So I'm going to bring these terms over to the left if that's all right with you. So I'm going to add x to both sides, and so the x comes on over. And I'm going to subtract 12 on both sides, so minus 12, and so that comes over. So something like that is what you probably want to do. And you know, the first order of business, when I just ask you to solve a quadratic, I would definitely see if it factors. And at this stage, should have some pretty good number sense to just kind of look at that and figure out if it does. In this case, I would at least start it out with an x and an x, probably do a plus 4 and a minus 3, and that's looking pretty good. And you'll see this a lot. You know, factors set to 0 is a great position to be in, because now what we know from the zero product property is this factor can be 0, which would make the whole thing 0. And this factor could be 0, which would make the whole thing 0. And so that's what would cause balance here in this equation at this stage. And so what we do is we take each factor and set it to 0 to see what would make it. And I'm hoping you all agree that this would be negative 4, this would be positive 3, and you get your 2 solutions for the quadratic. I'm just going to go ahead and put both back in. Remember, the idea with solving an equation is finding what will keep it balanced. And if I put negative 4 in, negative 4 squared is 16. 12 minus negative 4 is 16. If I put the 3 back in, 3 squared is 9. 12 minus 3 is 9. So these are the only 2 values that will allow us to balance that equation. Okay, good one. Now we're going to do part B the correct way, and then I'm going to throw a little red flag at you there to see, just make sure that you don't do what I see as a common mistake with something like this. So, first order of business, before you try to shortcut anything or do anything, what you probably want to do is set it to 0. So that, again, it's just a quick default position there. Set it to 0, then form your strategy on how you're going to solve it. In this case, we're going to factor. Now, it doesn't factor like all these quadratic trinomials that we've seen before. You're not going to do 2 binomials, but it does factor nicely. And as a matter of fact, it's pretty straightforward because I have 2 terms and each one has an x in it. So this is more just a quick greatest common factor. So I'm going to pull out the x, and I have that right there. That happens to be the factored form of x squared minus 4x. 2 factors, both set to 0. So let's do that. X, set it to 0. Good to go. X minus 4, set it to 0, and we get x equals 4. And so this one already solved. Kind of just do this, and there's my solution set. And you can kind of see that 0 has to work here. 0 squared is obviously the same as 4 times 0. So that works nice. Again, if you set it to 0 first, then think of your strategies. Because, and here's the red flag, and I don't want to necessarily put this in your head if you didn't think about it, but I've seen students, there we go, sorry about that. So I've seen students over the years try to shortcut this a little bit by doing something like this. They would say, hey, wait a minute, there's a quick factor of x on each side, and if I divide by x, well, x squared divided by x is x, and 4x divided by, and hey, wait a minute, I get 4, and then I'm done. And yeah, I mean, to some degree, yeah, 4 does work, but the only problem is you divide by a variable factor. And that's kind of a no-no in working with equations, because what happens is when you divide by that factor, you lose the solution that came from that factor. So I don't know what you want to do here on your notes, but essentially in an equation, dividing by both sides is fine, but when you're solving for a variable, don't divide by the variable factor. You lose a solution. So I don't know, however you want to do that, that's your call. Okay, but very good. That's why I like setting it to 0, because then I wouldn't even think about dividing by x here, because obviously you couldn't. All right, guys, letter C. Now here's a good high-level factoring problem, and it's here's where I would really strongly encourage you to pause the video and try it on your own. Can you factor something like that right there? I will tell you it does factor. You can use the method that I taught you on one of the previous notes worksheets. You can use whatever method works for you. But in essence, everybody, I need you to be able to factor something at that level. So can you make that happen? That's a great question. So pause the video for a moment. See if you can come up with that piece. And I'll kind of tell you what you should have gotten. All right, well. I saw this. I did a little trial and error on this when I did it myself. And the 15x squared, I kind of did a 5x and 3x when all was said and done. And the 12 there, I think the combination that works is a 6 and a 2, if I remember correctly. Because I have a 10x and an 18x, and that is probably going to work there. So I'm thinking a plus 6 and a minus 2. And I think that's going to do it. If you were unable to get to this stage, again, please pause or put a question mark by it and come back and ask. But basically now at this, if you've gotten there, hopefully it's all downhill, because now I would just set my factors to 0 and solve. Subtract the 6. I'll do this in 2 steps for you. And divide by the 5. So negative 6/5. There's one answer. Here, guys, add the 2. And then, of course, divide by the 3, and there's your second answer. So your solution set looks something like this. If I plugged either of those back into the left side and right side, perfect harmony there. I like it. Okay, so nice. Just being able to solve a quadratic by factoring. Notice in each stage I set it to 0 first and then went to town on it. Okay. Method 2, guys. Undoing the square. So this one happens to be very, very conditional. So let's be very clear on this. So it says on your paper, use this method when there is no middle term. So when there is no bx term there. If you think about that quadratic, you'll see both of the parts here where we can do it in just a second. Or when there is what is called, and you've seen this phrase once or twice already, what is called the square of a binomial. So those are the only 2 times we can do it. If it's in straight up standard form like you saw on example 1 there with those factoring problems, those are not candidates for undoing the square. Undoing the square is basically taking the opposite operation of squaring, which means you're square rooting. The one thing we have to be careful of in this case, when you undo a square, we're going to take both of the square roots of the number, the positive and the negative. And so what I think I'll do just very, very quickly is show you why that works, and then we'll go ahead and do A and B. And these go by pretty quick. So first of all, just all you have to do is watch here for a second. You don't have to do anything. If I asked you to solve something like this equation right here, and you were basically to say, hey, what number squared would give me 9? You would probably know exactly what the solution set is. Well, if you didn't, this is the way it would kind of work out. We would undo the square, meaning we would square root. So, undoing operations by taking its opposite, undoing the square, the opposite operation is square root. So the good news is, when you do this, that just gets x. You get the variable by itself. Now, here's where we kind of go into this piece. When we undo a square, well, the principal square root is 9. But there are actually 2 square roots of 9, one positive and one negative, because 3 squared gives me 9, but also negative 3 squared gives me 9. And so to honor the fact that 2 answers would work here, both the positive root and the negative root, we have to include the plus or minus when we undo that piece. And this is a very specific situation, but you do this a lot. So when you undo a square, just kind of get that in your head, you have to go ahead and take the plus or minus. Okay, well, let's go solve. So this would be a quadratic equation. Notice there's no middle term. There's no x term there. So that's what allows us to kind of just solve this in a little more straightforward manner, meaning I'm just going to undo the operations. I'm going to undo adding 20 by subtracting 20 to both sides. I'm going to undo multiplication by 4 by dividing by 4. So I'm just going to undo all the operations, kind of working from the outside in. Minus 20, divide by negative 4. And now, guys, the last thing to undo, of course, is the square. And I undo the square at this stage. Root 5 is an irrational number, so you're going to leave it. But please do not forget to include the plus or minus. And there you go. So root 5 works, and the negative of root 5 works. Wonderful. Now here is the other form, and we're going to see this on the back side as well, where this is a great little technique. So in this case, I have x minus 2, a binomial, squared. And that's what that phrase represented, by the way. And if you notice, I can solve for the variable pretty well here because this is in pretty user-friendly form by just working with the opposite operations outside in. I'm going to undo the square. So if you would, guys, so I'm going to square root, square root. In this case, you just get the x minus 2. And over here, again, because I undid the square, I'll take the positive 3 and the negative 3. And then the only thing to do at this stage would be to add 2 to both sides. So I'm going to add 2 to both sides. These would cancel. And it just depends on how you see this, of course, but it's 2 plus 3, and it's 2 minus 3. So these two combine together in 2 different ways. Addition of the 3 and subtraction with the 3. And so anyway, long story short here, 2 plus 3 is definitely 5. 2 minus 3 is negative 1. And so those would be your 2 answers when all said and done, because I can combine those together. And let me just go back really quick and just make sure that works. That's the good thing about this. You can always check. So let's try 5. 5 minus 2 is 3. 3 squared is 9. Negative 1. Negative 1 minus 2 is negative 3. Negative 3 squared, also 9. And that was the idea. So we had to honor the fact that both roots would work on that. Okay, so just be careful on undoing the square. It's great, but you have to make sure that you can only do it on those candidates. Okay, let's get into the completing the square piece. And if you've seen completing the square before, great. I'm going to sort of teach this as if you haven't seen it before. So I'm going to try to be a little visual with it. Bear with me on it if you don't mind, because there's one piece I need you to be able to do really perfectly as we go forward. And it is something we're going to use off and on over the course of this semester. This technique does get utilized, so it's not a one and done by any means. Anyway, it says complete the square on the following diagrams, use the following tiles. So maybe you've seen these before. I'm just going to draw them out. This would be what we would call an x squared tile. So x times x is x squared. Hey everyone, this is what is called an x tile. It would be a 1 by x. And 1 times x is x. So draw that in there for me. And then the last one is to do just a little unit tile, just a little 1 by 1, because 1 times 1, of course, is 1. And what we're going to do is just construct some diagrams using those tiles right here. And I like the phrase that goes along with it. Basically, I'm going to need to know what do I need to complete the square? That's the idea. What do I need to complete the square? So let's draw the three diagrams in. I happen to be artistically challenged, so this is going to look pretty disastrous up here, but maybe you'll get it to look nice on your paper. But I think it should still work. So here we go. This is what I'm thinking, at least initially, everyone. Give me one of those x squareds. So, and you can, in fact, kind of put the x squareds in there. And then give me an x tile like that. And we're going to just keep layering them vertically and horizontally. And that's your first diagram right there, by the way. So an x squared and an x is laid out that way. Okay. Next one. Just trying to keep these pretty straightforward. You can do these quite a bit more complex than I'm doing. But in order to get the pattern that we're looking for, I don't think we have to overplay it too much. So anyway, now if you don't mind, can you layer 2 vertically and then 2 horizontally? And then as I said, just keep it in the back of your mind here. What I'm going to ask you is, what do we need to complete the square? And then last one, guys, let's go ahead and do it one more time. So give me a nice x squared tile right there. And then let's get 3 going vertically. And yikes, that's not good looking, but whatever. And then let's go 3 horizontally right below here, just like that. Okay. And so the premise is, geometrically, what am I going to need? How many tiles and of what tiles am I going to need to complete the square? So let's write this out algebraically, and then let's go piece by piece. So if you kind of look at this nice diagram here in terms of the tiles that I have a single x squared. And by the way, we will always complete the square from a single x squared perspective, so that's good. So x squared, I hope you see we have 2 x's. So I would add the 2 x's, and these don't obviously morph together somehow. And then guys, put a little blank on the back. We'll do a lot with the blanks. And the question, of course, becomes, what do I need to complete the square right here? Well, I'm hoping you agree that all I have to do is add a little 1 right in there, and I've got a great looking perfect square. A little 1 by 1 tile does the trick. And so as a matter of fact, I add a unit tile on there. And as a matter of fact, we've created what is called a perfect square trinomial. And we'll talk about why we create that momentarily. Okay, but before, let's go into the next one. I guess I would ask you, what would you put in here to perfectly complete the square? Well, I think I'm seeing a 1, another 1 by 1, another 1 by 1, and another 1 by 1. So 1, 2, 3, 4 unit tiles right there. So I had an x squared, I had 4 x's, and in order to complete the square, everybody put a blank on the back, it looks like I needed 4 unit tiles to pull it off. Okay, good. Last one here. It looks like I have an x squared, I have a 6x, and everybody give me a blank, if you would, on the back. And what do I need to pull this off? Well, let's see. I'm going to need a little 1 by 1 in there, another 1 by 1 in there, and a ton of these 1 by 1s. Sorry, getting a little messy on that. I'm just going to do it dotted so you can kind of see. But 1, 2, 3, 4, 5, 6, 7, 8, 9. And as a result, I need 9 unit tiles to complete the square. And so here's the question, of course. As you're going to have to do this, how do I complete the square from these first 2 terms? And we're always going to complete the square off these first 2 terms, here and here and here. How do I complete the square on the first 2 terms without having to draw these diagrams here? Because certainly I don't want to have to do this again and again. So let's see if we can figure it out numerically. And that obviously is the next question on your notes worksheet here. It says, how do we find the constant that will complete the square? If you've seen it before, maybe you know. If not, I'll give you a hint. It has to do with this b value right in here. So this number right in front of the x, this coefficient, we call it the b value. Do something to do to this to get to that. Do to this to get to that. Do to this to get to that. If you kind of notice, the 1 and the 4 and the 9 are all perfect squares, aren't they? I think I kind of gave that away by saying perfect square trinomials. This is 1 squared, this is 2 squared, this is 3 squared. So if you kind of take a look at it, it looks like I would have to divvy this up by 2, then square it. Divide that by 2, then square it. Divide that by 2, and then square it. And that's it. As a matter of fact, we take our b, divide it by 2, and then square. All right. We're going to get just a touch of practice on this. Again, we'll get into the solving piece momentarily, but one step at a time. So before I can have you do example 4, which is obviously to go back and solve some quadratics, I need us to be able to do example 3 in that we have to essentially complete the square and then factor it. And you'll see why and how all this plays out. So let's go for it. So what goes in the blank to complete the square? Everybody, if you need to, grab a calculator, but you take the b value and you divide it by 2. So negative 14 divided by 2 is negative 7. And then you square negative 7. Don't forget, when you square a negative, it still turns out positive. So it's always going to be a plus, always. So plus 49. Negative 7 squared is positive 49. All right, now the whole reason for doing this is because of how it factors. So watch this unfold if you would. I'm going to do it longhand and then kind of do the shorthand. If I asked you to factor it, you would probably do x and x. That's good. And then you would think of two numbers that multiply to 49 and combine to negative 14, and I know you would come up with x minus 7, x minus 7. Do we want to necessarily write it as x minus 7, x minus 7? No. So this, as you can see, and we've seen this once or twice before, is that right there. And now it looks like what we called it as the square of a binomial. So what we're going to do is try to change our expression so it is quite a bit more user-friendly, and that should allow us to solve for our equation, solve for the variable. I would encourage you not to use decimals or mixed numbers. In this case, I think improper fractions work out great. So here's what I'm thinking for letter B. Obviously, 2 doesn't evenly go into 7. But I would take 7 and divide it by 2, and then I would square it. And so in this case, we've seen this before, by the way, quotient raised to a power. In order to remove the parentheses here, you would take 7 squared and 2 squared, and that would be it right there. So one more time, 7 over 2, and then square it. Leave it like this if you would, because I think that allows us to do this piece. Now the whole reason for doing this is because if we were to factor it, well I should say when we factor it, it's the same factor times itself. So the question is, what times itself would give me this right here? Well, we all know, of course, x times x is x squared. And we would look at this and be like, what times itself is 49 over 4? Well, guys, obviously it's the 7 over 2. So this is going to be 7 over 2, because 7 over 2 times 7 over 2 is 49 over 4. And if it has to add to that 7x right there, then it has to be a plus right here. So this would be x plus 7 halves times x plus 7 halves. And if I was to FOIL that out, lo and behold, I would get this right here. Okay, good. Some hard ones. Let's do letter C, and then we'll kind of get back in and just solve a couple real quick and round out this notes worksheet. So it would be great if you could pause for a second, see if you can do it all the way through. Hard one here. How would you complete the square? And then when you form that nice perfect square trinomial, how would it factor? Okay, well, when I did this, 1/2 divided by 2, kind of like that, is really the same thing as 1/2 times 1/2. Remember, kind of dividing by a number is the same as multiplying by its reciprocal. So long story short, this should be 1/4. And then you square 1/4, I'm getting a 1/16. If that explanation didn't do it justice, let me know. But 1/2 divided by 2 is 1/4, and 1/4 squared is 1/16. This is a nice perfect square on the back, as you can see. And again, the whole reason for doing this is because of how it factors. X times x would give me this. 1/4 times 1/4 would give me that. And it would have to combine to a positive in the middle. So it's going to be plus and plus. And so it's x plus 1/4 times x plus 1/4. Fantastic. So why did we take the time to do all that? Well, it comes down, I guess, to example 4 for right now. And we would go back to solving quadratics. And at this stage, we only have a couple methods to look at. But let's go over those methods. So I would look at this initially, and it's great. It's set to 0. I'm liking it. My first instinct would be to ask myself, does it factor? So can you think of two numbers that multiply to -6 and add to +4? No, it doesn't factor. So unfortunately, method 1, factoring, is out. Doesn't work. Method 2 would be undoing the square. And is this a candidate for undoing the square if there is this x term right in between? Absolutely not. So we can't undo the square. So what we need, obviously, is an alternative approach. And in my opinion, this completing the square is a great approach at that. Because now what we're going to do is complete the square off of the first two terms. So everybody, here's how it's going to play out. X squared plus 4x, put the blank on the back. Now, quite frankly, that 6, in my opinion, is in the way at this stage. You're going to move it to the other side. Now, notice what I did, and I sort of did it intuitively. We are working with an equation. So when I fill in this blank right here with whatever, because it's an equation, I have to keep everything balanced. So I'm going to do the same thing on the other side. So everyone, think about this for a moment. What would go in the blank in order to complete the square? So 4 divided by 2 is 2. 2 squared is 4. If I add 4 to the left-hand side of an equation, I have to balance it. It's probably one of the biggest mistakes I would see with something like this, just forgetting to keep everything in equilibrium. And that sort of speaks for itself. Now, again, what we're trying to do here is create something that is more user-friendly than this form up here. And by adding the 4 and then factoring it, I think we've done exactly that. The whole reason for completing the square is because of the way it factors. If I asked you to factor this right here, you would all tell me just x plus 2 times x plus 2, or really just x plus 2 squared. And then easy as can be, 6 plus 4 is 10. And so now you can see, and I'm just going to go back a screen or two, this form, doesn't it look exactly like this equation we had originally? And you can see it just now becomes undoing a square. Because all I have to do is undo that square, subtract the 2, and I'm in business. And so that's what we do. So guys, if you would, square root, those will cancel right here, and I get x plus 2. Don't forget, when you undo a square, plus or minus, root 10 is irrational, keep it as such. Minus 2, so the 2 moves over onto the other side. I hope you don't mind me shortcutting this just a touch, but the 2 goes over. And just be careful on the sign. When the 2 goes over, we would subtract, so it becomes negative. And guys, that's it. Those are the two answers there. Those are the two solutions to this quadratic. Not pretty by any means, but just as valid as any other of the good ones that we've seen. Hey, it would be great if you could pause just one more time and try letter B. So here we go. Letter B. I do x squared minus 8x. I always complete the square from the first two terms, and I do want a single x squared, which we have. So I put my blank on the back. The 11 is going over. And I put a blank on the back because I'm going to put something on the left. I'm going to balance it on the right. Hey, everyone, I'm going to add 16, and I'm going to add 16. So negative 8 divided by 2 is negative 4. Negative 4 squared, though, is positive 16. Okay, now again, the whole reason for completing the square is because it factors so nicely. If I asked you to factor this, you would probably all tell me x minus 4 times x minus 4. And so that really is x minus 4 squared. Negative 11 plus 16 is positive 5, and we are in business. Very, very user-friendly at this stage because all I have to do is undo the square, undo the -4, and and I've got it. So square root, x minus 4 equals, don't forget the plus or minus, square root of 5, and how about we add 4 to both sides here, guys? And when I add 4, there's your winner. Two solutions, both irrational here, both work. So get a little practice on that completing the square. We're going to continue this on the second notes worksheet. And just a reminder, you will need the quadratic formula program from me. So just before going on to the next notes worksheet, just track me down and I'll link it up. It only takes a couple seconds. So thank you very much for listening. Get a little practice on it and help each other out. And please don't hesitate to ask questions of me as well.